This video is about finding the derivative as a function using the definition of the derivative. So first, let's state this definition of the derivative. We call it f prime of x, and it is the limit as h approaches 0 of f of x plus h minus f of x, all over h. And this is provided that that limit exists. Let's do some examples. Let's find the derivative of y equals 2x squared. So what that is asking us to do is find the function that represents the slope of the tangent line for every point along the curve y equals 2x squared. We're going to use the definition of the derivative. So f prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. And all I've done there is copy down the definition of the derivative. Now I will plug into it. So this is the limit as h approaches 0. When I see f of x plus h, that means look at the function f, which is up here. I guess we should have called this f of x, but we know y is the same thing as f of x. We understand that. We're going to plug in x plus h everywhere we saw an x before. So this is 2 times x plus h squared minus, now we need f of x. Well, that's just rewriting the original function, 2x squared, and this is all over h. If we were to stop right now and try to plug in, we would see plug in a h goes to 0. That would cancel this h right here. So we'd be left with 2x squared minus 2x squared on the top, so a 0 on the top, and a 0 on the bottom, which remember, that's indeterminate. So that is an indeterminate form, which means we've got more work to do. We need some sort of algebra trick to help us out. And it looks like our algebra trick here is try to multiply things out and see what happens. What we'll see is some stuff is going to cancel. So the limit as h approaches 0. This is 2 times, I'm going to FOIL that x plus h. So that's x squared plus 2xh plus h squared. Pause the video and make sure you can multiply that out correctly, and then come back. And then 2x squared, nothing happens to that, so minus 2x squared all over h. And now I'll multiply that 2 over, so this is the limit as h approaches 0. Multiplying that 2 into everything, I'll get 2x squared plus 4xh plus 2h squared, and I still have that 2x squared hanging out on the end, all over h. And I look, things are canceling. 2x squareds cancel, and I can keep moving. So let's come up here. This is the limit as h approaches 0. I have 4xh plus 2h squared all over h. And if I do a quick spot check, I'm still at the point where if I plugged in a 0 for all my h's, I'd cancel out to 0 over 0. That's a problem. I don't want 0 over 0. I need something better than that to happen. So what I see I can do, and this should happen all the time on these, because where h is approaching 0 and causing the numerator and the denominator to go to 0, you should be able to eventually factor out an h on both the top and the bottom. And I see I have 4x plus 2h left if I pull an h out of the top, and then just my h on the bottom, which is great because now they do cancel. And I have the limit as h approaches 0 of 4x plus 2h. Now that those h's have canceled, I should be able to just plug in. So when I plug in an h of 0, I get 4x plus 2 times 0, which is just 4x. Which means this is f prime of x. This is the function that describes the derivative of 2x squared, or the slope of the tangent line for every part of the curve 2x squared. Now, a couple things to notice on notation. Notice I kept writing the limit part every time. I can't stop writing the limit as h approaches 0 until I've actually taken the limit. But once I've taken that limit, I no longer write it. So that's sort of a notational thing. One thing I like to compare this for people, let's just kind of come to the side over here for a second. If I asked you to find 2 plus 3, you would tell me, oh, that's a 5. And we all know that. 2 plus 3 is 5. But where did the plus go? We don't write the plus in our answer, right? That makes no sense. we just write the 5 because we've done the operation of addition. We don't need the addition anymore. We've done that operation. So what that kind of boils down to here is you need to keep the limit stuff in until you actually find a limit. It was between these two steps that I found the limit, so I no longer have to write my limit anymore. The limit as h approaches 0. I found my limit. It's no longer there. Just like over here, I added, so the plus is not in my answer. All right, so let's keep going. Let's do another example. Let's find the derivative of y equals the square root of x. Okay, so again, we're going to use the definition of the derivative. We're using that for all of these. So this is the limit as h approaches 0. Oh, let's scooch this over just a little. This is f prime of x is what I'm finding. It is the limit as h approaches 0 of f of x plus h minus f of x all over h. And that's where we're going to start each time we do the definition of the derivative. All right, now I need to plug in. This is the limit as h approaches 0. If I plug in x plus h everywhere I see an x, I see the square root of x plus h minus, and now I need to subtract f of x. That means just rewrite f of x down as it is. Remember, y is the same thing as f of x. And this is all over h. And now that I plugged in, if I take a moment to plug in, try to take my limit, try to evaluate it, I would plug in a 0 for my h's. But notice when I plug in a 0 for my h's, this just changes to square root of x, which cancels on the top, x squared of x minus square root of x to 0. And I'm ending up with 0 over 0, which is indeterminate, which means there's more work to do. Okay, so I can't stop there. I haven't actually found the limit. What I've found is the indeterminate form 0 over 0, which gives me a clue there's more work, and often that more work is some sort of algebra trick. When I see square roots, the algebra trick that comes to mind should be using the conjugate. So square root of x plus h minus the square root of x all over h. And I'm going to multiply by the conjugate, which is the square root of x plus h, now plus the square root of x. And I have to do that on the top and the bottom. I can't just run into a function and change just part of it. If I'm going to multiply by something, I need to multiply by 1 to keep it the same. So I need to do the same thing on the top and the bottom. So now this is the limit as h approaches 0. And I'm going to multiply out the top. I will be foiling, technically, because I have this times this two pieces binomial times this one. Take a moment and pause the video and make sure you can do that multiplication, because something nice is going to happen, and it will be easy to clean up. So the square root of x plus h times the square root of x plus h is just x plus h. The inner and outer are going to cancel, and I'm going to be left with minus x. And then the bottom, remember our rule of thumb is don't multiply the part you didn't set the conjugate up for. Just kind of leave it multiplied out. It'll make it easier because we expect to have some factoring and canceling happening later. So I have that. Okay, so if I notice now, this positive, use the eraser, sorry. This positive x and that negative x are going to cancel when I add them together. So this is the limit as h approaches 0. I only have an h left on top now, and on the bottom I have h times square root of x plus h plus square root of x, which is nice because I finally get those h's to cancel, which, remember, that was my goal, was to get those h's to cancel, because then I'll be able to plug in. So this is the limit as h approaches 0 of now just 1 over square root of x plus h plus the square root of x. Now I'll plug in my h approaches 0. Since I'm actually taking the limit, I'm plugging in that h is 0. I no longer have to write the limit anymore. So this will be 1 over square root of x plus 0 plus square root of x, which I can clean that up. That's 1 over square root of x plus square root of x. And I can actually clean that up one more step. I have 2 square root of x's, so this is 1 over 2 square root of x. And this is my derivative, f prime of x. All right, let's keep going. Let's now find the derivative of y equals 1 over x squared. So again, I always want to start I'm going to write the f of x for f prime of x f prime of x equals, the derivative equals the limit as h approaches 0 of f of x plus h minus f of x all over h. So this is the limit as h approaches 0. Now f of x plus h, I will plug in an x plus h everywhere I see an x before. So this is 1 over x plus h squared. Notice it looks a lot like my original. I just replaced the x with an x plus h. Minus, now just write down f of x, 1 over x squared. And then this is all over h. And if you take a second to try to plug in, you are going to get 0 over 0, which means do more work. We have not found the answer. Do something else. Remember that something else with 0 or 0 is generally some sort of algebraic manipulation. So the algebra I'm going to do here is getting a common denominator. So this is the limit as h approaches 0. So my common denominator, I have x plus h squared and I have an x squared here. They're both going to be in my common denominator. So what I can think about, let's see, I have ones in the top. What I can think about is I'll multiply this one by an x squared, which means the top has to be multiplied by x squared. And this one needs to be multiplied by the x plus h squared, so that its top has to be multiplied by the x plus h squared. And that gets the common denominators. And then I don't want to forget, this is all over an h. And I'll deal with it in just a minute. I'm trying to clean up that numerator first. So this is the limit as h approaches 0. I can combine the top now. This is x plus h squared times x squared. And I have x squared minus x plus h squared. And then one thing I'm going to do real quick, I'm dividing by h. That's the same thing as multiplying times 1 over h. That just makes life a little bit easier for me without having to write so much mess anymore. So that's like multiplying that whole thing by 1 over h. All right, we still need to do some algebra. I'm going to multiply out that numerator and see if things clean up, which hopefully they should if we've done things correctly. So this is the limit as h approaches 0 of x squared minus, and now I need to FOIL x plus h squared, so that's x squared plus 2xh plus h squared all over x plus h squared, x squared. I'm just going to throw the h there. I can just kind of move it into the denominator, right? Multiply by everything. So this is the limit as h approaches 0. I'm going to distribute that negative. So x squared minus 2xh minus h squared all over x plus h squared h. And now good things are happening. The x squareds cancel. So this is the limit as h approaches 0 of negative 2xh minus h squared over x plus h squared h. And you should see that I can factor an h out of the top now. That's kind of where you want to get to. So this is the limit as h approaches 0 of h times negative 2x minus h. Just pulled an h out of both parts of the top. X plus h squared h. And those h's cancel, which remember was my goal here. So this is the limit as h approaches 0 of negative 2x minus h in the top, x plus h squared times x squared in the bottom. Now, I should be able to find that limit as h approaches 0, which means plug in a 0 in for my h's. So I don't have to rewrite limit as h approaches 0 anymore. I'm finding that limit. So this is negative 2x on the top when h goes to 0, and then an x squared times an x squared on the bottom. So that's negative 2x over x squared times x squared is x to the 4th. I added those. I didn't multiply them. And this is negative 2 over x cubed. I can simplify that. And so let me just kind of write this up a little nicer. F prime of x is negative 2 over x cubed. So my derivative is negative 2 over x cubed. All right, let's do another one. Let's find the derivative of x over x minus 1. So again, f prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h, which is the limit as h approaches 0. So I'm plugging in x plus h. So I get x plus h over x plus h minus 1 minus x over x minus 1, right? That's my f of x. And this is all over h. So kind of like last time, you get a common denominator. This is the limit as h approaches 0. We can get that common denominator. I'm going to do just a one step this time. X plus h minus 1 minus, times x minus 1. That will be my common denominator. So my numerator will be x plus h, and x plus h needs to be multiplied by the x minus 1, and then minus x, which needs to be multiplied by the x plus h minus 1. And this is all over h, which remember our little shortcut is just multiply times 1 over h, so you don't have such a big mess going on with your fractions. Unless you like the big mess of a fraction, that's fine too. Limit as h approaches 0. I got some foiling to do now, so pause real quick and do all the multiplying out and see how it goes, then come back and check and make sure you're getting the same thing I am. So this is what? X squared minus x plus xh minus h. And now I'm going to distribute that minus x squared minus xh plus x all over, rewriting that denominator, x plus h minus 1 times x minus 1, and that 1 times h, well, that h can just go down there now, multiply it in, make life just a little bit simpler. Now, things should cancel. Let's see what happened. Yeah, I see an x squared and a negative x squared. I see a negative x and a positive x. I see a positive xh and a negative xh. Wow, like pretty much everything canceled. So I have the limit as h goes to 0. All I have left on top is a minus h. And then on the bottom I have x plus h minus 1 times x minus 1 times h. And this is good because we finally get those h's to cancel. That means we can plug in a little better now. So this is going to be the limit as h approaches 0. I have negative 1 left on top. X plus h minus 1 times x minus 1 on the bottom. So this is the limit as h goes to 0 of negative... Oh, hold on. Sorry. I'm just recopying things without paying attention to what I'm doing. I don't have to write that anymore because what am I doing? Now I'm plugging in. I've got those h's to cancel. I can let h go to 0. So that's negative 1 over x. Well, if you let this h go to 0, I'm just left with x minus 1 right there. And then another x minus 1. So this is negative 1 over x minus 1 squared is my derivative f prime of x. That's how we'd normally write it. We would combine those two to make them look a little nicer. So there's a bunch of examples of finding the definition or finding the derivative using the definition of a derivative. Let's talk about just a couple other things real quick. Some notation. So for a function y, which is f of x, we can denote the derivative as, well, one of these we've just been using, f prime of x. So we say f prime of x is how we say that. And then we can also say just y prime. That's another pretty common one. We can also call this, have dy dx. So you're just going to say dy dx. What this one means is the derivative, that's what the d kind of is, derivative of y with respect to the variable x. Later on, or if you're taking multivariable calculus eventually, you might be taking the derivative of a function with lots of variables, so you want to be very specific of what variable you're differentiating with respect to. It might be differentiating with respect to x, with respect to z, with respect to w, just, who knows, whatever you're doing. Those that we're looking at that I just wrote, those are really the most common. We also might say, let's see, df, dx, that would come up too, or the derivative with respect to x of the function f of x. That's also a pretty likely possibility. All right. When do we not have a derivative? We're not going to have a derivative at a corner, somewhere like that. Notice if you were thinking about like the slope of the point on the left side, that tangent would look sort of like that. The slope on the right side, its tangent would look like that. They're different tangents, if you will. They're not meeting up with each other. So we're not going to have a derivative. Similar, something like this. We call that a cusp. There's not going to be a derivative. If you have a function that kind of does that, and what we have here going on is a vertical tangent, there's not going to be a derivative there. And then if you have some discontinuity, or, there's my graph, or, an infinite discontinuity because of an asymptote, or you just have a hole, those are not going to have derivative either. Okay. And let's just talk about now just a couple comparisons. Let's let f of x equal x squared. Let's graph f of x and f prime of x. So we're going to graph something and its derivative and just kind of compare them for a minute as well. Okay. So let's find f prime of x first. F prime of x, remember, is the limit as h goes to 0 of f of x plus h minus f of x all over h, which is the limit as h goes to 0. If I plug x plus h in, this is x plus h squared minus x squared all over h. And hopefully notice we need to do some algebra, because if we plugged in a h go to 0 now, we would get 0 over 0. So let's do some algebra. I'm going to multiply things out. FOIL that first part. And divide by h. If you didn't follow along with that, pause the video and make sure you can FOIL that out and get the same thing I did. That's nice, because now those x squares are canceling. And I have the limit as h goes to 0 of 2xh plus h squared over h, which that's looking good, because I see I can factor an h out of the top. And that will cancel with the h in the bottom. So I'm finding the limit as h goes to 0 of just 2x plus h, which if I take that limit, if I let h go to 0, I'm just left with 2x. So my derivative, my slope, my f prime of x is 2x. So let's graph both of these at the same time. So and I'm going to take that and copy it real quick. Well, if it'll let me. Okay. So I'm going to graph f of x up here and f prime of x down here. So f of x is that just x squared. So it goes through the point 0, 0. It goes through 1, 1. It goes through 2, 4. It's just kind of our real basic parabola. So it looks kind of like that. Okay. And now I'm going to graph f prime of x. that was, remember we just found was y equals 2x. And this one was x squared. So 2x is a line. It's going to, add the eraser. 2x is a line. It's going to go through the origin with a slope of 2. So rise to run. It's going to go kind of like that. Almost perfect. Okay, close enough. So let's compare these for just a second and talk about the tangent lines. So let's look at negative values for my original function. So I'm looking kind of over here. Notice all of these, the slope is going to be negative. The slope of these tangent lines, like if I drew a tangent line here, if I drew a tangent line here, if I drew a tangent line here, these all have negative slopes. And notice that corresponds down here to negative values. Okay, so negative slope in the original is going to be negative values of the derivative. And then let's think for a minute, what's going on here right at 0? It looks like I have a perfectly horizontal line. That would be a slope of 0 at 0. And notice at 0 down here, I have a value of 0. So a slope of 0 in the original function corresponds to a value of 0 on the derivative. And then lastly, looks like these are positive tangent lines over here. And then, so these are positive slopes. And these are positive values. So when you're looking at a picture of something and its derivative, if the original has negative slopes, then your derivative will be below the x-axis. If your original has a 0 slope, it will be going on the x-axis. And if your original has positive slopes, like these values over here, your derivative will be above the x-axis. So that's a way you can kind of think about how those are related to each other.